Dear students, welcome back to the lecture series on solid state. In this session, we will discuss two important methods based on diffraction, namely electron diffraction and neutron diffraction by crystals. Before moving on to today's session, let's discuss the assignment questions of the previous class. Let's begin with the first question. The atomic scattering factor of an atom primarily depends on. We have four options. Option A, the number of protons in the nucleus. Option B, the distribution of electrons around the atom. Option C, the crystal structure of the compound. And option D, the number of neutrons in the atom. In the last class, we discussed about two important concepts used in X-ray crystallography, namely atomic scattering factor and structure factor. The atomic scattering factor describes the scattering by a single atom, and it determines how strongly an atom scatters the diffracted beam. So, the atomic scattering factor of an atom primarily depends on the distribution of electrons around the atom. Greater the number of electrons in an atom, greater will be the scattering power of the atom, or greater will be the atomic scattering factor. So, the correct option is option B, the distribution of electrons around the atom. Now, we will move on to the second question. At small scattering angles, the atomic scattering factor is approximately equal to option A 1, option B atomic number represented as Z, option C half of the atomic number or half of Z, option D 0. We have seen that the atomic scattering factor depend upon the angle of scattering, that is theta. At small scattering angles, the scattering factor is approximately equal to the atomic number, or that is equal to the, when theta equals 0, F is equal to the number of electrons in the sample. So, the correct option is option B, atomic number. And as theta increases, what happens? Let us find out. So, that is question number 3. As the scattering angle theta increases, the atomic scattering factor F. You have four options. Option A, increases linearly. Option B, decreases gradually. Option C, remains constant. And option D, first increases, then decreases. So, as the scattering angle theta increases, the atomic scattering factor F decreases gradually. So, what happens when theta increases? When theta increases, there will be diffractions or scattering from all parts of the electron cloud. They may interfere in a destructive manner, thereby reducing the overall amplitude. So, this causes a decrease in the value of the atomic scattering factor. So, as the scattering angle theta increases, the atomic scattering factor decreases. The correct option is option B, decreases gradually. Now, we will move on to the fourth question. The structure factor FHKL represents option A, the scattering from one electron, option B, the scattering from one atom, option C, the combined scattering from all atoms in a unit cell, and option D, the diffraction intensity from one crystal plane. Okay. The structure factor is another important quantity that we discussed in the previous class. When atomic scattering factor denotes the scattering by a single atom, the structure factor describes the combined scattering from all atoms in a unit cell. So, here the correct option is option C, the combined scattering from all atoms in a unit cell. The structure factor determines the intensity of the diffraction peaks, and it describes the combined scattering from all atoms in a unit cell. Next question. The intensity of an X-ray diffraction peak is proportional to option A FHKL, option B modulus of FHKL, option C modulus square of FHKL, option D 1 by FHKL. We have seen that the intensity of a diffraction peak from a particular plane is proportional to modulus of FHKL square, or the square of the structure factor. So, the correct option is option C, FHKL square. Last question. The term e raised to 2 pi I hxj plus kyj plus lzj in FHKL expresses option A scattering power of an atom, option B phase difference between the scattered waves, option C absorption coefficient, option D lattice parameter. In the last class we have seen that mathematically the structure factor FHKL can be represented as summation j equals 1 to n Fj, which is the atomic scattering factor, into e raised to 2 pi I hxj plus k yj plus l zj. So, here h, k and l are the Miller indices and x, y and z are the fractional coordinates. So, the fractional coordinates. So, in this term Fj, we know that Fj represents the atomic scattering factor. In the second term, you can see the Miller indices plus the fractional coordinates describes the position of the atom. So, that term, that is the exponential term e raised to 2 pi I hxj plus kyj plus lzj represents the phase difference between the scattered waves. Okay. So, the correct option is option B, phase difference between scattered waves. So, now we will move on to today's session. In the previous classes, we have discussed about the diffraction of X-rays by crystals. That is, we have seen that crystals can be used as diffraction gratings for X-rays. And we have discussed two methods, namely rotating crystal method and the powder method or Debye-Scherrer method based on X-ray diffraction. So, what is diffraction? It is a property of the matter waves or the electromagnetic radiations. And when this diffraction occurs? Diffraction occurs when a wave encounters a regular repeating structure like atomic planes in a crystal. We know that crystalline solids are characterized by a well ordered arrangement of its structural units. So, when there is such a regular repeating structure, then and a electromagnetic wave or a matter wave interacts with such planes, then diffraction occurs. And constructive interference give rise to diffraction maxima as described by Bragg's law, that is n lambda equals 2d sin theta, where lambda is the wavelength of the electromagnetic radiation. Here if it is X-rays, then the wavelength of the X-rays, n is the order of diffraction, d is the spacing between the atomic planes, and theta is the diffraction angle. So, similar to X-rays, we know that X-rays are electromagnetic radiations. So, similar to X-rays, electrons and neutrons, they can also show diffraction, but they interact differently with matter. Okay. So, in this figure you can see X-rays falling on a crystal, they are getting diffracted and producing characteristic diffraction pattern. So, in a similar way, electrons and neutrons also show diffraction, or in other words, we can say that crystals can also act as diffraction gratings for electrons and neutrons, similar to that for X-rays. But the only difference is that the electrons and neutrons interact differently with matter. So, let us begin with electron diffraction. The diffraction of electrons is based on the wave nature of electrons as proposed by de Broglie, that is de Broglie hypothesis in 1924. We know the well known de Broglie equation, that is lambda equals h by mv, where lambda is the wavelength, h is the Planck's constant, m is the mass of the particle, and v is the velocity. So, mass into velocity is the momentum. So, this can also be written as h by p. So, de Broglie hypothesis, lambda equals h by mv, that is a matter exhibits both particle as well as wave-like nature. So, when accelerated through a potential difference, they acquire a wavelength, that is the electrons acquire a wavelength comparable to the interatomic distances. So, when they acquire a wavelength comparable to the interatomic distances, they can be diffracted by the crystal lattice, just like X-rays. Why crystals act as diffraction gratings for X-rays? Because their wavelength is comparable to the spacing between the atomic planes. So, in the case of electrons, when electrons are accelerated through a potential difference, they acquire a wavelength comparable to the spacing between the atomic planes. So, electrons can also be diffracted by the crystal lattice. So, this is the basic principle of electron diffraction. The wave nature of the electrons was confirmed by Davison and Germer in 1927 by the well known Davison-Germer experiment. And in the experiment, the electrons are reflected from a nickel crystal and they showed maxima at specific angles. On the screen you can see a nickel crystal. A beam of electrons is incident on the nickel crystal and they get diffracted, which is fallen on the photographic plate. Okay. So, nickel crystal, the electrons reflected from the nickel crystal showed maxima at specific angles, and this was the first experimental support to prove the wave nature of electrons, and this gave a direct proof of de Broglie hypothesis. And in the Davison and Germer experiment, the observed diffraction pattern perfectly matched the Bragg's law predictions. Okay. So, this was the first experimental support to prove the wave nature of the electrons, that is electrons can also be diffracted by crystals, and it matched the Bragg's law condition. Now, let us see how this electron diffraction method works. We need a diffraction grating. So, when we deal with crystals, the crystalline material acts like a diffraction grating, scattering the electron beam. Now what happens when electrons falls on the crystal? There will be scattering. So as the electrons pass through the sample, they interact with the positively charged atomic nuclei. We know that electrons are negatively charged particle. So when they falls on the crystal, they interact with the positively charged atomic nuclei and the electron clouds surrounding the nuclei, causing them to scatter in different directions. Okay. So the crystalline material or the crystalline solid can act as a diffraction grating, scattering the electron beam. And how these electron beams are scattered? When electrons pass through the sample, they interact with the positively charged atomic nuclei and the electron cloud surrounding the atomic nuclei. So this causes the electron beam to scatter in different directions. The scattered electrons then interfere with each other. So either they can interfere constructively or destructively, creating a diffraction pattern of bright and dark fringes on a detector screen. And the final step is the data analysis. The pattern of spots and rings is unique to the crystal structure of the material, and this can be used to identify the substance and determine the precise positions of its atoms. So this is how the electron diffraction method works. We have a crystalline solid which act as a diffraction grating. The electrons falling on the crystal interact with the atomic nuclei as well as the electron cloud surrounding it, and it scatters in different directions. The scattered electrons undergo constructive as well as destructive interference, producing a diffraction pattern of bright and dark fringes on a detector screen. And these diffraction spots are analyzed, and this is a fingerprint or a signature of the crystal's internal structure, and hence it can be used to identify the substance and determine the precise positions of its atoms. So this is an experimental setup for an electron diffraction technique. We need a thin crystalline sample of approximately 100 nanometers thick. The source of electron beam is from an electron gun accelerated at 20 to 200 kilovolt. The electrons are allowed to transmit through the sample and they are diffracted. The pattern is observed on a detector screen, which is generally a fluorescent screen or a photographic plate. So this setup is similar to that of a transmission electron microscope, commonly called TEM. Okay. So here you can see an electron gun which produces a beam of electrons. They are allowed to pass through a slit and then allowed to pass on to the sample. And here you can see the diffraction rings on the photographic plate or a fluorescent screen. And through the gun, the electron beams are accelerated through 20 to 200 kilovolt. Now let us see different types of electron diffraction methods. The first one is low energy electron diffraction or LEED. So as the name suggests, in low energy electron diffraction method, we employ low energy electrons, usually in the range 20 to 500 electron volt, and their wavelength is generally in the range of 0.05 to 1 angstrom. So in this method, the electrons again are allowed to fall on the crystalline solid or the sample, but here the electrons do not penetrate deeply into the atomic nuclei. They interact only with the top few atomic layers, and hence we may say this method, that is the low energy electron diffraction method, is a surface sensitive method. Why? Because the electrons do not penetrate deeply into the crystal lattice, they interact only with the top few atomic layers. So it is generally used for studying the surface morphology or surface changes. So, we may say that it is a surface sensitive method. So, as I said earlier, it is used to determine the surface structure, adsorption as well as surface reconstruction. As we discussed earlier, in this method, that is in LEED method, this also consists of an electron gun. We need a sample, that is a crystal surface, and again the detector is a fluorescent screen showing the diffraction spots. So, this is about the low energy electron diffraction method or technique, in which low energy electrons of generally 20 to 500 electron volt is used, with wavelength ranging from 0.05 to 1 angstrom, which is comparable to the spacing between the atomic planes. And here the electrons do not penetrate deeply, they interact only with the top few atomic layers, and hence it is a surface sensitive method, and it is generally used to determine the surface structure, adsorption and reconstruction. The next method is reflection high energy electron diffraction or RHEED, and this method of electron diffraction is also used for studying surface structures. And here a high energy, so generally in the range 10 to 100 kilo electron volt, electron beam strikes the surface at a very shallow angle. The diffraction pattern is then recorded on a suitable screen. This method is commonly used to monitor the growth of thin films in molecular beam epitaxy, as the diffraction pattern changes with surface layer formation. Okay. So, this method, that is reflection high energy electron diffraction method, is also used for studying surface structures, especially to monitor the growth of thin films, because the diffraction pattern will change with changes in the surface layer formation. Okay. So, here a high energy electron beam is employed, generally of 10 to 100 kilo electron volt, when it strikes the surface, and that is at a very shallow angle, and diffraction pattern formed is recorded on a fluorescent screen or a photographic plate. So, this is about the two types of electron diffraction techniques, namely low energy electron diffraction and reflection high energy electron diffraction. Let us see the general applications of electron diffraction method. It is widely used in the determination of crystal symmetry and the identification of lattices and calculation of lattice parameters. It is also used for the study of surface structures, namely particularly LEED and RHEED. And this electron diffraction method is a direct proof of the wave nature of electrons. LEED as well as RHEED, two types of electron diffraction methods, are widely used in the analysis of thin films and also in the nanoparticle analysis. So, these are the applications of electron diffraction method. Now, we will see another diffraction method, namely neutron diffraction. As we discussed earlier, along with X-rays, electrons as well as neutrons show diffraction. So, when we consider neutrons, we know that neutrons are neutral particles, but they possess a magnetic moment. The wavelength of the thermal neutrons, that is the neutrons slow down to thermal velocity, is approximately equal to 1 to 2 angstrom, which is comparable to the spacing between the atomic planes. So, in neutron diffraction, they use slow thermal neutrons with wavelengths comparable to the atomic spacings. And here, when neutrons fall on the crystal planes, they are scattered by the atomic nuclei and not electrons. Okay. So, in neutron diffraction, the neutrons are diffracted or scattered by the atomic nuclei and not electrons. Neutron diffraction method is also based on Bragg's law, that is n lambda equals 2d sin theta. So, all three diffraction methods we discussed so far, that is whether it is X-ray diffraction, electron diffraction or neutron diffraction, all is based on the Bragg's law, or they satisfy the Bragg's law condition n lambda equals 2d sin theta. Okay. So, when we come to neutron diffraction, we have seen that they use slow thermal neutrons with their wavelengths comparable to the atomic spacings, and the neutrons are scattered by atomic nuclei but not electrons, and it satisfies the Bragg's law. And since neutrons are neutral, they have the ability to penetrate deeply and scatter mainly by the atomic nuclei. So, this makes them ideal for locating light atoms and also for studying the magnetic order. While we discussed about the electron diffraction, electrons were not able to penetrate deeply into the atomic nuclei or into the crystal lattice. They can penetrate only up to the top few layers of the atomic planes, and hence they are suitable only for surface related studies. But when we come to neutron diffraction, they are able to penetrate deeply and scatter mainly by the atomic nuclei, and hence they can be used for locating light atoms and for studying the magnetic order. So, this is the experimental setup for neutron diffraction. We have a source of neutrons generally from a nuclear reactor or a spallation source. Now, the neutrons from the nuclear reactor are generally slowed down to their thermal velocities by passing through a moderator, generally a graphite moderator. A graphite moderator is used in order to slow down the neutrons to their thermal velocities. Then we have a monochromator for selecting the desired wavelength. We have a collimator in order to get a very narrow beam. The sample can be either a crystal or a powdered sample, and then we have a detector which measures the intensity versus the angle, diffraction angle. So, in this figure you can see an incident neutrons from the source nuclear reactor passing through a slit and falling on the sample. And here, similar to that of a rotating crystal method, the powdered sample or the crystal can be placed on a rotating disc so that you can rotate this in every possible direction. So, the neutrons falling on it will get scattered or diffracted. The diffracted beams are detected by the detector. Okay. So, this is about the neutron diffraction experimental setup. Now, let us see the applications of neutron diffraction. The scattering of the neutrons mainly depend upon the properties of the nuclei. So, that means each nuclei scatter the neutrons in a different way. So, this technique, that is the neutron diffraction method, helps in locating light atoms like hydrogen, lithium, boron, etc. When we deal with X-ray diffraction or electron diffraction, we know that the scattering power is equal to the number of electrons in the atom. Number of electrons in the atom. So, when we consider light atoms like hydrogen, lithium, etc. For hydrogen there is only one electron. For lithium there are only 3 electrons. So, when we consider light atoms, since the number of electrons is less, they scatter very weakly. We know that the scattering power is equal to the number of electrons. Greater the number of electrons, greater will be the scattering power. So, for light atoms, they scatter very weakly. So, if we employ neutron diffraction, they can penetrate deeply into the atomic nuclei, and hence we can easily locate light atoms like hydrogen, lithium, boron, etc. It is also used for studying the magnetic structures. Another application lies in the analysis of isotopic composition. We have seen that the scattering of neutrons depend upon the properties of the nuclei. So, when we consider the isotopes of hydrogen like protium, deuterium and tritium, we know that the 3 are different nuclei. So, neutron diffraction method can easily distinguish these 3 isotopes. Why? Because the scattering of the neutron depend upon the properties of the nuclei. So, this method helps in the analysis of isotopic composition. This is also used to investigate residual stress and strain, and also to determine complex molecular and biological structures. So, this table shows the comparison of the 3 diffraction methods, namely X-ray diffraction, electron diffraction and neutron diffraction. So, the first feature is about the interaction. X-rays interact with the electron cloud, electrons interact with the atomic field, whereas neutrons interact with the atomic nuclei and their spins. About the penetrating power. X-rays can penetrate deeply, whereas electrons, they cannot penetrate deep into the crystal lattice, only on the top few layers. So, we may say it is a shallow penetration, whereas neutrons can penetrate deeply into the atomic nuclei. About surface sensitivity, X-rays have a very poor surface sensitivity, whereas electrons or electron diffraction is very excellent in surface sensitive methods, and neutrons also have very poor surface sensitivity. Now, about detecting the light atoms, X-rays are very poor in detecting the light atoms, because we know that there will be lesser number of electrons, then the scattering power will be less. Whereas electron diffraction, it is about partial in detecting the light atoms, whereas neutron diffraction is very excellent in detecting the light atoms, because they can penetrate deeply into the atomic nuclei. Now, about the magnetic information. Magnetic information is possible only in neutron diffraction method and not in X-rays and electrons. So, these are the properties of the 3 methods, X-ray, electron as well as neutron diffraction methods. So, in this session, we have discussed about 2 diffraction methods, namely electron and neutron diffraction by crystals. All diffraction methods rely on the wave particle duality of matter. Electron diffraction are generally used for surface studies and the analysis of structures of thin films. The electron diffraction methods, particularly the low energy electron diffraction or the reflection high energy electron diffraction, are widely used in surface crystallography or surface studies. Neutron diffraction is particularly useful in the study of light atoms and also magnetic ordering. So, together, that is both electron diffraction and neutron diffraction, they reveal complete picture of the crystal structure. Now let's discuss some assignment questions. First question, electron diffraction experiments confirm option A, the particle nature of electrons, option B, the wave nature of electrons, option C, the dual nature of light only, option D, the charge to mass ratio of electrons. Second question, low energy electron diffraction is primarily used for determining bulk crystal structure, investigating the surface structure of crystals, analyzing amorphous materials, measuring magnetic moments. Third question, which diffraction technique is most suitable for monitoring thin film growth in real time? X-ray diffraction, TED, RHEED, that is reflection high energy electron diffraction, and LEED. Fourth question, neutron diffraction differs from X-ray diffraction because neutrons interact with electron clouds, neutrons interact with atomic nuclei, neutrons are charged particles, neutrons have no wavelength. Fifth question, neutron diffraction is most useful for locating heavy metal atoms, electron densities, light atoms like hydrogen, crystal vacancies. The last one, the magnetic structure of crystals can be best studied using X-ray diffraction, electron diffraction, neutron diffraction, and infrared spectroscopy. Please try to find out the answers. We will discuss it in the next class. Thank you.